Okay, welcome back, class. Extremely sorry for my very crowded desktop, but now let us switch on attention to the subject. Okay, so this is the unit of LDPE and HDPE. I hope you know what is LDPE and HDPE is. Please bear with me for the signatures and this tiny Godzilla over here. Okay, let's pay attention. Okay, preparation, properties, and application of polymers. See, basically in this semester, fourth semester, you just need to know preparation, then properties, and then application of various polymers. So let us first consider polyethylene. It was first produced in England by the Imperial Chemical Industries (ICI) in the year 1933 by addition polymerization of ethylene monomer. So you take a ethylene monomer, you polymerize it, then rapid addition of the monomers gives you the polymer. So addition polymerization is the process of repeated addition of monomers that possess double or triple bonds to form polymers. Okay. Ethane is catalytically degraded to form ethylene. So ethane is catalytically degraded to form ethylene because ethane molecular formula is C2H6, but ethylene molecular formula is C2H4. That's why there is a double bond. Okay, which is a gas at room temperature, mainly classified into two categories: low density polyethylene and high density polyethylene. So low density polyethylene is molecules with branches, high density polyethylene is linear. So if you think logically, then the reason low density polyethylene has branches is because when you have branched arrangement, then you cannot have compact packing. But when you have a linear arrangement, you can have a compact packing, and that compact packing leads to high density. Now, the industrial plastic widely utilized are manufacturing by large number of monomer molecules, which are covalently bonded. Okay. Each atom within a molecule is capable of forming van der Waals interaction with an atom from another molecule. Larger is the chain length, greater is the melting and the boiling point. So this we all know, larger the chain length, greater is the melting and the boiling point. If we consider a typical example of polyethylene plastic, it has two types, LDPE and HDPE. LDPE के characteristics है A. Branch chain polymer, B. Highly insoluble in organic solvents at room temperature, highly inert and non-reactive in nature. So therefore, whenever you carry the low density polyethylene bag and carry substances like food grains and all, so it doesn't react with them. So you carry tomatoes, you carry brinjals, you carry potatoes, you carry eggplant, so they don't react with the polyethylene. Okay. High tensile strength, chemical and moisture resistance. So definitely you can even carry water in the polyethylene bags. Extremely flexible because it's moisture resistance and non-polar. So non-polar means consisting of molecules not having a dipole because there is no electronegativity difference. Because Non-polar molecules occur when electrons are shared equal between atoms of a diatomic molecule. Now, these are the characteristics of LDPE. Now let us see the applications. We all know the application of low density polyethylene, packing and wrapping, frozen food, squeeze bottles, domestic water storage, due to non-polar nature used as a cable insulation also. Preparation of LDPE. Produced by the high pressure 1500 atmosphere. Polymerization of ethylene using oxygen as the initiator at 200 to 250 degrees Celsius. So just remember this terms or the values or of pressure and temperature. 0.1% of O2 is sufficient to initiate the polymerization. Manufactured by bulk or suspension polymerization technique, where benzene or chlorobenzene are used as solvents. The molten polymer is chilled below its crystalline melting point, and it is partially crystalline in nature. The density of such plastic is in the range of, this is very important, know the density of LDPE. It is soluble in many solvents such as toluene, xylene, CCl4, carbon tetrachloride above 100 degrees Celsius. The branching of the polyethylene LDPE occurs either by the intermolecular or intermolecular chain transfer. So what is intermolecular chain transfer? When there are two different chains of two growing polymeric chains, two growing polymer molecules, and there is a transfer between these two chains. In this case, this H molecule is going here, and this is getting all the valencies satisfied CH3, and the molecules, what it is we call that free radical site, is getting stabilized. So this is a dead chain now, and here in this case, one H went here, so this is having a free radical site now. So this radical site is shifted over here. So this is the intermolecular chain transfer. So this is how the branching has occurred. Because now a new molecule will join here, so branching will be there. Now intramolecular chain transfer. So it happens within same polymeric chain of the same molecule. So this is the growing polymeric chain, and there is a transfer here. One H molecule goes from here to here. This gets satisfied because all the four valencies of carbon are satisfied. So the free radical side is here. So now here the new chain will join, and there the branching will occur. So branching of polyethylene occurs either by, especially LDPE, occurs either by intermolecular or intramolecular chain. I hope you understand this. Just read it, you will know. In first case, the branches will be longer because the number of backbone chain may be more or less. So here the branching will be longer because the backbone is can be more or less, right? In second, the branches will be shorter in length because it is happening by intermolecularity. So naturally, in this case, there are four, so there will be four in the backbone only. So branch won't be that big, larger. Branch will be the branches will be fixed, means four carbon atoms in the back. But here it could be five, six, seven, anything. Physical and chemical properties of LDPE. Now this is interesting. Dependent on variables like molecular weight, degree of polymerization, and short or long chain branching. So how are the physical and chemical properties of LDPE decided? Because they are decided depending on the variables like molecular weight, degree of polymerization, short or long chain branching, degree of crystallinity. It is Q equals to QC plus QA. which is QC, is the degree of crystalline substance present in the polymer, and QA is the degree of the amorphous substance in the polymer. The addition of them is the degree of crystallinity. Crystallinity refers to the degree of structural order in a solid. In a crystal, the atoms or molecules are arranged in a regular and periodic manner. The degree of crystallinity has a big influence on hardness, density, transparency, and diffusion. Density of a material increases when it changes its phase from liquid to crystal. Naturally, liquid substance has low density, solid substance has high density. Amorphous component in a polymer are in the liquid phase, and the crystalline component are in crystalline phase. In our case, density of plastic is low, hence low crystallinity, that is 40 to 50%. Most of the physical properties are dependent on crystallinity, such as stiffness, hardness, tear strength, chemical resistance, softness, and yield point. All these properties increases with increase in density or decreasing amount of short chain branch, and so does the molecular weight. Because if there is a decreasing amount of short chain branching, then there will be compactness increasing. More compactness means more density. If the molecular weight increases, also the density increases. However, and with increase in density, all these properties increase like stiffness, hardness, stress, chemical resistance, softness, and yield point. However, electrical and mechanical properties are quite good and desirable for specific end use. Like I said, LDPE can be used for cable insulation. Chemical nature is inert, does not dissolve in chemical solvents at room temperature. Even the solvents in which LDPE is soluble in toluene, carbon tetrachloride, it is above 100 degrees. So at room temperature, it hardly has any impact. It ages to exposure to light, heat, and oxygen with loss of strength, elongation, and tear strength. Yeah. High density polyethylene. Now we shift our attention to HDPE. Most commonly synthesized by coordination polymerization of ethylene, supported by metal oxide catalyst dissolved in heptane. So, what is coordination polymerization? Coordination polymerization is a form of polymerization that is catalyzed by transition metal salts and complexes. Ziegler-Natta is used in coordination polymerization. If you go back in your third semester lecture of Ziegler-Natta, you'll understand what it is. Pressure is applied to the reaction vessel at 50 to 70 degrees. Cooled and made powder of granules. Polymer is filtered, washed and dried. Properties: it is 90% crystalline, linear chain polymer containing 200 carbon atoms in the main chain. Melting point is about 135 and the density is in the range of 0.95 to 0.97. Because of higher crystallinity and density, it is more stiffer, harder, and have more tensile strength. Chemical resistivity either retained or improved as compared to branch chain polyethylene LDPE. Low temperature brittleness and low permeability to gases and vapors are also improved in the linear material. High density polyethylene much stiffer than LDPE, high tensile strength and hardness, storage of chemical and volatile liquids, manufacture of toys and other household articles. Application polypropylene has some properties as polyethylene, but it is less resistant to oxidation properties, heat, and light. Due to excellent dielectric properties and moisture resistant, it is used in parts of refrigerators other than TV and radios. Polystyrene also has inert nature, quite less as compared to the above two. However, thermal depolymerization is possible and can be soluble in many organic solids. So see, HDPE is even better than these two, polypropylene and polystyrene. Application of HDPE. Due to stiffness and hardness, it can be used for storage of many dilute and concentrated chemicals. It can be used to store hydrofluoric acid, which can even corrode the glass materials. So you see, even the glass can get corroded by hydrofluoric acid, but HDPE does not get corroded. Production of bottles and big container. Due to excellent resistance towards environmental stress cracking, it is used for detergent bottles. About 20%, about 25% product is used in injection molding of crates, plates, cubes, caps, closures, houses. Crates are nothing but plastics. Uh, you know, they are plastic containers. You can keep vegetables in that crates. Okay. Higher heat resistance and hence used for wires and cable insulation materials, along with non-polar nature for fabrication of film sheets and pipes. Application of polyethylene for fabrication of film material for packaging and wrapping food. The high flexibility without incorporation of pastas makes them suitable for squeeze bottles. Pipes made up of LDPE are extensively used for agriculture, irrigation, and domestic water line connection. Non-polar in nature makes them suitable for insulating material. Extrusion coating for packaging material is the second largest market, accounts 10% of demand from US, also for lamination. Lighter in weight, hence used for many household things. So extrusion coating is the coating of a molten web of synthetic resin onto a substrate material. That's lamination. Acrylic resin or plastic. So acrylic resin or plastic. The acrylic family of resin embraces all products formed by the polymerization of monomers, which are in effect derivatives of acrylic acid. CH2 double bond CHCOOH. Example: polyacrylic acid, polymethyl acrylic acid, polybutyl methacrylate, polymethyl methacrylate. Most important plastic in the family is polymethyl methacrylate, which is polyacrylic acid. If you polymerize polyacrylic acid, you will get polymethyl methacrylate, or the derivative of acrylic acid. If you polymerize it, you will get polymethyl methacrylate. This is polyacrylic acid. The ester of this polyacrylic acid constitutes an important group in plastic. So if I just add an ester group to it, CH2CH, ester group COOR, COOR, R is the CH3 here, so it becomes polymethyl methacrylate. Acrylic resin or plastics. The methacrylate monomer are obtained from the action of acetone and hydrogen cyanide and the proper alcohol at 150 to 160 degrees Celsius in traces of concentrated H2SO4. So this is our acetone, and then hydrogen cyanide is there. So we get this intermediate product, and then in presence of concentrated H2SO4, further reaction we get methyl methacrylate. So this reaction is quite tough to understand. So you have to take a page and paper and then start writing it. And if there is any difficulty, then you can ask me. Synthesis of polymethyl methacrylate is normally prepared by emulsion or solution polymerization. In emulsion polymer, the water-insoluble monomeric acrylic derivatives are emulsified and then polymerized. So what are the monomer in this case? While preparation of polymethyl methacrylate, acrylic derivatives. So they are emulsified and then polymerized in emulsion polymers. Typical agents commonly used are carboxylic and sulfonic acid soaps or sulfonated long chain alcohols, amines, and surfactants. So these are emulsifying agents which are being used. Generally, catalyst added to accelerate the formation of polymerization nuclei. Example ozone, persulfates, and peroxides and oxygen. In solution polymerization, the methyl methacrylate monomer may be diluted with enough solvents and then polymerized. The typical solvents are benzene, acetone, and alcohol. The solution polymerization product is dependent upon few factors, that is temperature, catalyst, concentration of catalyst, and nature of the solvent. Now properties of PMMA and also application. It is a colorless transparent plastic with an excellent outdoor life period and good strength. Due to presence of bulky groups, ester groups are bulky in the molecule, it is amorphous in nature. It is resistant to many chemicals but readily soluble in organic solvents like ketone and esters. It can be thermally degraded, yielding back to entire quantity of monomer. Due to its crystal clear transparency, it can be transmit it can transmit the light and hence utilized in making surgeons light, advertising displays, and decorative novelties. The high internal reflection property make their use for the manufacture of reflectors to mark the edge of the highway. Yeah, edge of the highway. You must have seen on the roads. Due to transparency along with the strength and lighter weight, PMMA is used in lenses and windows of airplanes and also for keeping human mandibles. Human mandibles are like the bone, the skull, the jaw of humans, right? So to keep them, we can use PMMA. It has great resistance towards shock. When shattered, the acrylic sheet breaks into dull edge pieces which are not practically dangerous. So if you shatter a glass, you will get fine edges pieces which are very dangerous. But if you shatter an acrylic sheet, it will break into dull edged pieces which are not dangerous. PMMA exhibit excellent resistance to salt solution, dilute acids, alkalis, minerals, animals and vegetable oils, and aliphatic hydrocarbons. It dissolves in aromatic hydrocarbons, esters, and ketones. So it is resistant to all these, but it is getting dissolved in aromatic hydrocarbon esters and ketones. When ignited, it burns with a luminous flame. Common interesting application of PMMA is fabrication of shockproof glass called flexite. Luminous flame means that shines in the dark. However, compared with glass, it has poor scratch resistance. They have more or less involved in typical polymer applications, that is coating adhesive, impregnation of fabrics or paper, textile, finishing or printing. Impregnation means to soak or saturate with a substance. So this is all regarding 4.1, unit number 4.1. The next part we'll see later. I hope you understand this much. That reaction is very important of production of PMMA. These practices, this reaction.